Hey everybody, let's have a look at diodes basic introduction today. Here's the symbol for a diode, and you can see that I have written anode and cathode, and above the cathode is a negative, above the anode is a positive. What this means is that in order for this diode to actually conduct and act like a closed switch, we would have to orientate our power supply relative to the cathode and the anode. So just to back up a little bit, a diode is a PN junction, and if we have the power supply correctly orientated, it will decrease the depletion region and cause the diode to conduct. And diodes only pass current in one direction. When they're passing current, we call it forward bias, and it's operating like a closed switch. In order for the diode to conduct, we actually have to have the negative of the power supply connected over here at the cathode, the positive of the supply connected at the anode, and we have to include a load or we just end up with a dead short between our positive and negative on our power supply. A typical silicone diode needs about 7.7 volts just in order to work, and it will drop 0.7 across it when it is conducting. If it was germanium, it would be roughly 0.3 volts when it's conducting. Now down here, I have two examples. In the top example, the diode is correctly orientated for forward bias. So that is the negative of the power supply is connected to the cathode, the positive of the power supply connected on the anode side. This would mean that the diode would be conducting, and if we were looking at conventional current flow, the conduction would flow from positive out around through the load and back into negative. If we look at electron flow theory, it flows out of the negative into the cathode, around through the load and back. Don't worry about the direction of current flow. Where that came from was a long time ago when they were trying to figure things out. They thought it was conventional flow from positive to negative. Scientists today have determined where their theory is that it goes from negative to positive. It doesn't change the math or the fact that it conducts. Now I mentioned that a silicon diode chews up about 0.7 volts, needs at least 0.7 volts to conduct. So if my supply here was 10 volts, my diode is conducting, it chews up about 0.7 volts. Then the load, because the diode and the load are in series, the load only gets 9.3 volts, which is fine. So again, connected like this, it's called forward bias. The diode will conduct, the load will be on, and the diode has a 0.7 volt drop. That means 9.3 volts is left for the load when we have a 10 volt supply. On this next drawing, I've connected it in reverse bias. So my negative power supply is connected to the anode, my positive of the supply is connected to the cathode. This means that the diode will be blocking. In other words, it's acting like a closed switch. Oops, it's acting like an open switch. It's blocking. And if we were to put a voltmeter across that open switch, all 10 volts of this supply would show up on the voltmeter. And there wouldn't be a current flow, which means that the actual load would be off with 0 volts across it. So again, connected like this, we call it reverse bias. The diode will not conduct, it's called blocking. The load will be off, the diode has a full 10 volts across it, and the load has 0 volts across it. Just a few more things that you should note. Diodes, if you're buying a diode, you would have to make sure that you match the diode you were buying to the application. The 3 things you need to look for: forward current rating, forward voltage drop, and peak inverse voltage. So the forward current rating is the maximum current that you could put across the load. Now this is a rating in AC, alternating current, and RMS, which is root mean square. In our example, I had connected it to 10 volts DC. In a later video, I'll teach you how the diodes work for rectification, to block the AC so that it only sends the current through the load in one direction. RMS, we talked a little bit about that, and that's what your normal multimeter will read on a given circuit. So it's root mean square. Now the forward voltage drop, that's your normal voltage drop, and I mentioned that it's 0.7 for silicone, 0.3 for germanium. And the last thing is peak inverse voltage, or what we call the PIV rating. And this is, I mentioned that in this scenario, when it's in reverse bias, it will block and act like an open switch. However, if you exceed the rating of that diode with too high a voltage, then yes, the diode can break down and conduct even though you weren't expecting it to. So that would be exceeding the peak inverse voltage, causing the diode to conduct even though it wasn't supposed to. And the maximum value of reverse voltage is measured in AC, and it's what's called instantaneous. And in AC, alternating current, we can calculate or figure into the sine wave exactly how much voltage at any given instance there is. Thanks so much for joining me today. I hope that was helpful, and we'll talk to you soon.